Wow, that water felt amazing. You guys should jump in.
Part 1. The ordinary afternoon. A teenager runs across a crowded dock. The sun is bright. Music drifts from a boat somewhere across the water. Around her, children are already in the lake, swimming between floating platforms, shouting, laughing. Her friends are below, waving her down. She jumps. She resurfaces laughing, wipes her face, pushes wet hair out of her eyes and swims toward the dock ladder. Nothing about that moment announces itself as unusual. Hours later, the headache begins. At first it feels unremarkable. Mild pressure behind the eyes, a vague heaviness, sensitivity to light. Most people assume dehydration after a long afternoon outside. The body still functions normally enough to ignore the signal, because early neurological irritation rarely announces itself clearly. There is no alarm. There is no pain disproportionate to the day. She goes home, eats dinner, mentions the headache in passing. The nervous system has already registered something, but the processing centers responsible for interpreting that signal are beginning to operate under conditions they were never designed to handle. The access point. Most people think of the nose as a breathing organ, something that filters air, gets congested, detects smell. The idea that the nasal cavity is also a neurological access point, a direct pathway connecting the external environment to the brain, rarely occurs to anyone. But the anatomy is precise. High inside the upper nasal region, past the areas affected by ordinary congestion, sits the olfactory epithelium, a thin, specialized tissue layer carrying nerve endings responsible for detecting odor molecules and transmitting them toward the brain. Those nerve fibers extend through microscopic openings in the cribriform plate, a delicate section of bone at the base of the skull, and connect directly to the olfactory bulbs positioned beneath the frontal regions of the brain. The arrangement exists because smell requires speed. Odor detection communicates with neural processing centers through the most direct anatomical route available. Naegleria fowleri finds that route. The organism does not enter through the mouth. It does not enter through broken skin. It does not circulate through the bloodstream seeking a way in. It enters through the nose, specifically when warm fresh water is forced upward into the nasal cavity, with enough pressure to reach tissue high inside the upper nasal region where the olfactory epithelium lies exposed. Diving, jumping feet first from a dock, underwater flips, water sports, sudden submersion at speed. These activities create the mechanical conditions capable of driving contaminated water beyond ordinary airflow zones into the deeper anatomical structures where sensory neural tissue begins. Once the organism reaches that tissue, it no longer needs to travel far. The critical distinction, and the reason primary amoebic meningoencephalitis progresses so rapidly, is that Naegleria fowleri bypasses the body's systemic filtering entirely. It does not need to survive the bloodstream. It does not need to breach multiple immune barriers across different organ systems. It migrates directly along sensory nerve pathways already connected to central neural structures. The distance between contaminated freshwater and brain tissue is shorter than most people could imagine. Swallowing the same water usually produces no danger. Stomach acid and digestive defenses create conditions hostile to survival. The critical exposure is nasal, and specifically high nasal, where ordinary physiology was never designed to resist what the organism is capable of doing next. Part 3. Silent progression. There is no pain when exposure occurs. A swimmer resurfaces, wipes water from her face, laughs. The brain does not produce an alarm because the earliest invasion occurs in microscopic anatomical spaces beyond conscious detection. There is no wound visible externally, no swelling that can be felt, no signal recognizable as danger. The person continues the day normally. Meanwhile, Naegleria fowleri has begun migrating along the olfactory nerve pathways toward the olfactory bulbs, neural structures positioned beneath the frontal brain. This is not a slow process. The organism is interacting with delicate tissue designed for sensory transmission, not for resisting aggressive microbial penetration. The olfactory system was optimized for sensitivity, not defense. Once the organism reaches the olfactory bulbs, it is no longer outside the central nervous system. Primary amoebic meningoencephalitis, PAM, takes its name from the resulting inflammatory process. But the word meningoencephalitis can feel abstract until the anatomy makes it specific. The meninges are the protective membranes surrounding the brain and spinal cord. Encephalitis is inflammation of the brain tissue itself. Both begin developing in the regions the organism has already reached. The infection does not require weeks of slow systemic spread before reaching neural tissue. It is already there. The early symptoms, when they arrive, feel completely ordinary. Headache, fever, nausea, fatigue, neck stiffness. These signals overlap with dozens of common illnesses: viral infection, heat exhaustion, dehydration. Most patients do not suspect a rapidly progressing brain infection after a normal recreational afternoon. Families do not connect the symptoms to the water because the gap between exposure and onset creates psychological distance. The cause and consequence feel unrelated. And while that psychological distance persists, the organism continues moving. Part 4. 2 simultaneous threats. Immune activation begins once invasion reaches neural tissue. Inflammatory cells migrate toward infected regions near the olfactory system. Chemical mediators trigger swelling responses designed to isolate and contain biological threats. This is the body behaving correctly, deploying the mechanisms evolved over millions of years to respond to microbial invasion. Inside the skull, those mechanisms become dangerous. The brain exists within a rigid enclosure with almost no excess space. Unlike tissues in other organs capable of temporarily expanding under inflammation, neural tissue inside the cranial cavity has nowhere to go. Every increase in volume translates immediately into pressure, and pressure, inside an enclosed space, compresses everything simultaneously. Blood vessels, neural tissue, cerebrospinal fluid dynamics, the delicate pathways responsible for electrochemical communication between billions of neurons. 2 threats are now developing simultaneously. The organism continues destroying tissue directly, migrating through neural regions, disrupting cellular integrity in the olfactory system and surrounding structures. At the same time, the immune response is generating edema that the skull cannot accommodate. Both processes are progressing in parallel. Both are damaging neural stability through different mechanisms at the same time. A healthy brain depends on uninterrupted electrochemical signaling across neural networks calibrated over years of development. Timing precision matters. Synchronization between regions matters. When swelling compresses tissue, that precision begins failing. Not because neurons are destroyed yet, but because the physical conditions required for coordinated communication are deteriorating. The person may still appear externally normal during this stage. Still speaking, still walking, still recognizing family members, still answering questions correctly. Visible neurological collapse consistently lags behind the biological progression already underway internally. The brain compensates aggressively during early dysfunction, rerouting, adjusting, masking instability, while inflammatory pressure continues increasing beneath the skull. Part 5. Pressure. Compensation has limits. As intracranial pressure rises beyond what auto-regulatory systems can offset, neural communication begins failing more visibly. The progression does not feel gradual from the outside, because the brain masks deterioration until it can no longer sustain the masking. Speech begins fragmenting in many patients. Words slow. Sentences stop completing correctly. Responses begin failing to match the questions asked. The neural networks coordinating language, connecting comprehension, memory retrieval, speech formation, and motor coordination are operating under increasing mechanical stress. The patient may still recognize familiar faces while no longer forming coherent verbal responses moments later. These are not subtle cognitive fluctuations. They are signs that organized electrochemical regulation across large neural regions is beginning to break down under pressure. Seizures become increasingly likely as electrical stability deteriorates. Healthy neural tissue depends on balanced excitation and inhibition across interconnected networks. Swelling disrupts those relationships. Damaged neurons begin firing abnormally. Inflamed tissue alters electrical thresholds across surrounding regions. Instead of coordinated signaling, unstable bursts of uncontrolled electrical activity begin propagating through circuits that were functioning correctly hours earlier. Muscles contract against conscious control. Eyes deviate involuntarily. Limbs stiffen. Awareness fragments. A seizure at this stage is not simply a symptom among others. It is evidence that the organized electrical regulation the brain depends on to maintain coordinated function is actively collapsing under escalating pressure and inflammation. Families witnessing this progression describe a quality of shock specific to the speed. Someone who mentioned a headache the previous day may now appear severely neurologically impaired, confused, agitated, failing to consistently recognize people they know. Hallucinations emerge. Emotional responses stop matching reality. Cortical systems responsible for stable interpretation of the environment are losing functional coherence rapidly. Part 6. Survival systems. The brainstem does not perform functions most people think about consciously. Breathing rhythm, heart rate regulation, blood pressure stability, swallowing reflexes, the maintenance of wakefulness. These systems operate continuously beneath awareness every second of life. They do not require conscious maintenance because they evolved to function automatically. Human survival assumes they will continue functioning without interruption. When swelling inside the skull begins compressing the brainstem, those assumptions stop being valid. Intracranial pressure at this stage has risen far beyond ordinary inflammatory conditions. Cerebral edema is expanding through multiple neural regions simultaneously while blood flow becomes increasingly compromised. The organism is still actively destroying tissue, but pressure itself has now become equally destructive, not through direct cellular damage, but through mechanical compression of structures that regulate the most fundamental survival processes. The emergency environment changes completely once severe neurological collapse begins. Physicians are no longer treating an infection in the conventional sense. They are attempting to manage pressure, oxygen delivery, electrical failure, impending brainstem compromise. Monitors display abnormal vital signs as the autonomic nervous system loses regulatory stability under worsening intracranial stress. Consciousness becomes unreliable. Protective airway reflexes weaken. Mechanical ventilation may become necessary because the patient can no longer reliably sustain breathing independently. Time has become the central variable. Naegleria fowleri destroys tissue quickly enough that many patients deteriorate significantly before definitive diagnosis fully confirms the responsible organism. Early symptoms resembled more common conditions: viral meningitis, bacterial infection, heat illness. And the clinical picture did not immediately suggest PAM, because PAM is rare enough that most physicians encounter it infrequently or never. Broad antimicrobial treatment may begin once severe meningoencephalitis is suspected, but treatment effectiveness decreases dramatically once widespread swelling and necrotic tissue damage have already developed. Brain tissue does not regenerate after severe destruction. Neurons lost to necrosis cannot be replaced the way damaged skin cells regenerate. Communication pathways built across years of neurodevelopment collapse permanently when enough tissue dies under sustained inflammatory and mechanical stress. Even among the extremely rare survivors of PAM, long-term neurological consequences depend on how much injury accumulated before stabilization became possible. Survival remains rare not because treatment options are entirely absent, but because the disease progresses faster than the clinical environment can reliably respond to it. Part 7. Confinement. The skull protects the brain from physical trauma. That same rigidity becomes lethal under sustained internal pressure. As swelling continues expanding, portions of the brain begin shifting inside the cranial cavity under pressure gradients. Neural structures are forced against rigid bone and through narrow anatomical openings that exist to allow blood vessels, cerebrospinal fluid circulation, and neural pathways to pass, not to accommodate displaced tissue under crisis pressure. Vascular compression intensifies. Oxygen deprivation spreads beyond originally infected regions into areas that had been functioning normally. Herniation describes what occurs when rising intracranial pressure forces portions of brain tissue into spaces where they physically compress critical structures. Once this begins, respiratory regulation, cardiovascular stability, and consciousness can collapse rapidly because the brainstem, the structure supporting all of it, becomes mechanically compromised. The body may still appear alive externally during this process. Machines maintain breathing. Medication supports circulation. Monitors continue displaying electrical activity. But inside the skull, the communication networks responsible for organized human function are being destroyed faster than any stabilization system can restore them. The patient is present in the room. The patient is no longer reliably present in the biological sense that makes presence meaningful. Cerebrospinal fluid dynamics have become disrupted under pressure. Cerebral perfusion continues falling. Metabolic waste accumulates around damaged tissue. The immune response remains active, still generating edema, inside an enclosed space that has no remaining tolerance for additional volume. What the immune system is attempting to do and what the brain can physically survive have stopped being compatible. Part 8. What ordinary assumed. One of the most psychologically destabilizing aspects of primary amoebic meningoencephalitis is not the severity of the outcome, it is the starting point. No wound, no toxic exposure, no violent event, no visible injury of any kind. Only warm fresh water forced into the nose during an activity millions of people engage in every summer without consequence. The exposure lasts seconds. The mechanism it initiates does not stop. Human intuition expects catastrophic outcomes to originate from catastrophic events. It expects the severity of a consequence to scale proportionally with the severity of the cause. Primary amoebic meningoencephalitis violates that expectation so completely that families often struggle to understand how a normal afternoon produced what they are now watching unfold inside an intensive care unit. The brain survives ordinary life because multiple protective systems normally separate neural tissue from the external environment. Bone, membranes, immune filters, blood-brain barriers. These systems function continuously without conscious awareness. People trust them the way they trust other invisible infrastructure, not because they have verified it, but because it has always worked before. The olfactory system was not designed to resist high-pressure nasal exposure carrying organisms capable of migrating directly along sensory nerve pathways into the central nervous system. That pathway was optimized for something else entirely, for the speed and sensitivity that smell requires. The vulnerability is not an accident. It is a structural consequence of how the nervous system is organized. Naegleria fowleri does not require toxins. It does not require broad systemic spread. It does not require days of circulation before reaching neural tissue. It requires one anatomical route, already connected directly to the brain, momentarily exposed to contaminated water under the right conditions. That is what makes the ending feel less like tragedy in the conventional sense and more like a quiet collapse of assumptions. Not the assumption that swimming is safe. The assumption that the brain is protected, that the skull is enough, that the biological systems operating beneath awareness every second are more robust than a single afternoon in warm fresh water can test. The command is sent. Nothing moves. Because the structures responsible for receiving the signal, for interpreting it, sustaining it, building the next thought from it, may already be under conditions from which organized function does not return. Most people swim through summer and emerge unchanged. The water recedes from the face. The afternoon continues. The brain operates normally, as it was always expected to do. What primary amoebic meningoencephalitis reveals is not a new vulnerability. It reveals something that was always present in the anatomy, a narrow passage between the external world and the most complex biological structure the human body contains. A passage that functions silently and correctly in almost every case,
Pathology of Fear is a medical documentary series presenting clinically documented neurologic and pathological mechanisms for educational analysis.